Hello students, so we'll solve a numerical of Cotter joint. So I'll read out the numerical. It is required, it is not completely visible in your screen I think, yeah, but still it is required to design a Cotter joint to connect two steel rods of equal diameter. Each rod is subjected to an axial tensile force of 50 kilonewton. Design the joint and specify the main dimensions. Okay, take factor of safety for socket and spigot, that is 6, and for Cotter as 4. Okay, so let's start. The given, what are given things are, say Cotter joint, you have to find out two rods are there, you have to connect the rods. Okay, both the rods are of equal diameter, so let's say the diameters are d, small d, they are of equal diameter. So we'll have to find out the dimensions of the Cotter joint so that it can take a load of 50 kilonewton. Okay, 50 kilonewton. So here force P is given as 50 kilonewton. Alright. Okay. Now factor of safety, Fs is 6 for spigot and socket. Okay, and Fs is 4 for Cotter. Normally, why is it given it as like this? Now see, higher factor of safety means we are applying lower forces, isn't it? If factor of safety is high means your allowable or permissible load is low. Okay, that means we don't want spigot or socket to fail, but rather if suppose failure happens, then it should fail, and your Cotter part will fail at the beginning, because for Cotter we have kept its factor of safety as 4. Okay, by the way, I think the materials are not given, so we'll take a material for all of them, spigot, socket and Cotter, as 30C8. So from a numerical we'll take this value, so this is also given to you. Okay, so 30C8 is your the plain carbon steel. This is a plain carbon steel, and this is the material which is given for your Cotter, and this is your ultimate yield strength in tension is given as 400 Newton per millimeter square. Okay, there is no information about ultimate strength. Okay, that means we have to solve the numerical to prevent your permanent deformation. Okay, yielding is the permanent deformation, right? So you see, factor of safety is 6 for socket. You have understood, because we have to keep keep the stress, allowable stress, very much below the failure stress. Now in this case the failure stress is, or failure strength here is 400 Newton per millimeter square. Okay, this is a failure stress or strength, you can say yield strength also you can call. So this is 400, so we'll keep it much below for both of them, but for socket and spigot we'll keep it 6 times less, and for Cotter we'll keep it 4 times less than this value. Okay, so let's find out the allowable values. Okay, now yeah, one thing that is not given, that is actually we'll take it like this. In general there is a theory actually, that theory you'll learn it later. If your SYT, that is yield strength in tension, is given, okay, to find out SSY, which is yield strength in shear, we'll find it using a formula or using a relationship given by a theory. It is called maximum shear stress theory, it is SSY. Okay, you can find it out, your yield strength in shear, we can find it out by multiplying 0.5 with SYT, that is yield strength in tension. So this will use it here in this formula, in this problem. By the way, this will be given to you in a question. Use this theory or the information like 0.5 times your shear, yield strength in shear is 0.5 times yield strength in tension. That information will also be given. Okay, now let's find out the allowable stresses. Allowable stresses for spigot, you can say socket, you write socket, and first you find out for socket. Now you see, you have seen socket can fail in two ways, right? This is the failure of the socket. Socket can fail in a tensile failure can also happen, and shear failure can also happen. Okay, forget about crushing here or compressive failure. We'll do only for tensile and your shear, tensile and shear. Yeah. So that means we have to find out the allowable, since we know the value of P, right? Isn't it? P is given, that is applied force is given. The applied force is given. We have to find out the allowable stresses, and from the area formulas we have to get the dimensions, because areas are, they comprise of the dimensions, isn't it? All the dimensions. So this diameter is a dimension, this thing is a, there will be some dimension. So we can find out what we are asked to find out the dimensions, right? So we can find out the dimensions from there. Understood? Okay, now you see, now for socket, let's find out the allowable tensile strength, tensile stress, not strength. So stress is equal to, now see how to find out allowable tensile strength. If you know the failure stress and if you know the factor of safety, then you can find out the allowable values, isn't it? Now because factor of safety is what? Failure stress by allowable stress. So failure stress or the strength here is SYT, because it is given here in this question. Okay, and no other information is given, like ultimate tensile strength is not given, right? So we have to prevent the permanent deformation. Okay, so now this is sigma equal to SYT divided by factor of safety. This is given as just like this. So sigma, you have to find out from here allowable tensile strength. This is your 400 divided by 6. Okay, from here you calculate it. Okay, and this is 66.67 Newton per millimeter square. Okay, then allowable shear stress. Okay, so allowable shear stress, now see, this is shear stress and this is what? Yield strength in tension. So we cannot use failure yield strength in tension here. We have to use the failure strength which is applicable for shear as SY. We write it right here. Okay, so allowable shear stress equal to this is failure strength which is yield in shear, okay, divided by factor of safety, right? So from here you can find out the allowable shear stress for the socket, which is, and now see, this is 0.5 times SYT divided by factor of safety. So 0.5 into 400 divided by 6. If you find out, then you will get it as around 33.3 here, 33.33. The values have been already found. I'm just explaining it. Okay, so now for socket spigot, similarly allowable stress, this is tensile stress which is same. Okay, this is your failure stress, okay, divided by factor of safety. So this is what? 400 and factor of safety is 6. This is 66.67, and allowable tensile strength is also same. Okay, 0.5 into 400 divided by 6, which is 33.33 Newton per millimeter square. Okay, here also Newton per millimeter square. Okay, now for your Cotter. Okay, for Cotter, there is only one type of failure. Okay, actually there is one more failure that I have not talked about it. The Cotter may bend also. Okay, so actually let's just explain that. I forgot to explain. The Cotter can break like this. Okay, fine, right, but it can also bend. If it doesn't break, okay, due to the forces like this, this is the Cotter, right? So there is P by 2 force, there is P by 2 force, there is P force. Okay, it may not break completely, but it can bend in this manner because of the forces, because these are the forces, so it can bend in this manner. So we have to prevent the bending of the Cotter also. Then if the Cotter bends, okay, then also it will be a failure. Okay, so from your bending stress formula we have found out a bending stress, and there is a formula for that. By the way, I will not go to the derivation here now. Okay, and I'll explain the formula here while taking the class. So this is actually, now you see all these formulas, this is force by something or movement by something we are doing here. So we'll have to find out the allowable stress first, then the moment or force will be given to you, and you have to find the safe dimension to prevent the failure. Okay, understood? That is what we are doing. Okay, now the safe dimension is actually, now see, now if we find out using that formula, shear stress equal to force by the failure area in case of complete breaking. Okay, then also we'll get some width of the Cotter is b with some value, in some value, let's say 3 millimeter, and thickness is, let's say, 1 millimeter. Okay, we'll get using this formula, and also using the bending we'll get b equal to, let's say, let's say 4 mm, and t equal to something which is 2 mm. Now which one will take? Okay, so in this case we'll get both to different values. Now the thing is, if we take 1 mm, this will be safe in case of what, breaking. Okay, but if we take 2 mm, then also it will be safe, isn't it? Okay, right? So the logic is, if you take higher value, okay, it will be safe for both the cases. Okay, so otherwise if you take a lower value, it will not be safe for in this case. Okay, right? So you always take the higher value. You have to find both, using both the formulas. You have to find out the dimensions and you have to take their higher values. Okay, so in this problem also you'll have to do that. Okay, by the way, that thing is my videos, I'll make it only 20 minutes or something. Okay, so this problem may continue later. Okay, so now okay, for Cotter you have to find out that since it is, there is a shear failure, so SSY by FS, okay, 0.5 times SYT by factor of safety, this is 0.5 into 400. Okay, 0.5 into 400 divided by 4. So from here we find out this is 50 Newton per millimeter square. Okay, now alright, so for bending case, okay, so there's a form. So okay, forget about the bending part right now. Okay, we'll talk it later. Right, so let's start solving. I'll explain for the first thing, that is your this one, failure of your Cotter or failure of your socket part. Okay, let's start solving for. Okay, one more type of failure I forgot to tell you, that see, if this is the complete assembly. Okay, what if this is the spigot which is inside the socket? Okay, fine. Now you are pulling it. What if your entire joint is intact, nothing happens to the joint, but your rod, one of the rod breaks here suddenly? Okay, that can also be a failure, right? So in this case, since the failure area, rod will fail like this, right? So here this is the area. Okay, so this will be what, the cross sectional area only for the rod. So from here we can find out the safe dimension of the rod. If you know the material of this, if you know, since this is a what, this area is perpendicular to the force, so this will be a tensile failure. So sigma tensile is equal to force by this failure, it is pi d square by 4. Okay, from here this is diameter d. Okay, this diameter is d. so P by this area. Okay, alright. So now from here you can find out, if you know this one, this value, then you can find out the diameter, safe diameter for the rod. Okay, now you see. Now let's find out using that formula. Now see, the thing is like that sigma T for the rod, since the Cotter is a part of spigot or socket, both are integral part of the rods, isn't it? And rods are made of same material. If this rod is made of 30C8, the socket will also be made of 30C8 because they are the same material. Similarly for this rod, 30C is the material, and the spigot part is also made of 30C8. Okay, so whatever the values are for your socket and spigot, okay, so they will be same for the rod. Okay, the rod here. So now sigma T for the rod. Okay, if you are finding out the diameter of the rod, safe diameter of the rod, okay, then sigma T is force by failure area. Okay, right, diameter of the rod is small d. Okay, now this is equal to sigma T is equal sigma T is your 66.67. this is 50 into 10 to the power 3 pi by 4 d square. If you solve this, you get the diameter as 30.9. okay, I told you don't make it 31 because you try to make the first digit even. Okay, so make it 32 mm. Okay, alright, done. Next, there are some formulas which are actually directly they are established and they are in use, okay, from long time. Okay, they are called empirical relationships. Empirical relationships. Actually, they are based on, these relationships are based on observations. Okay, like or human experience. Because design is a very old thing. Okay, people previously, okay, before civilization also they used to design. Even your people when they lived in caves, okay, then also they used to design their I can say weapons and all these things. Okay, weapons for hunting and all this. So those are also a type of design. Okay, so they did not do any dimensioning, right? But from there, at that time, I mean, people have invented your wheel and all these things. Okay, so they have observed something. Okay, it works like that, it works like that, and if you use this dimension, that will be useful for us, something like that. Okay, so some relations between some of the dimensions they have already developed. Okay, now there is such type of relationship is present. If we normally take the thickness of the Cotter as 0.31 times the diameter of this rod. Okay, so whatever is the diameter for the rod you get, okay, you multiply 0.31 with that dimension and to get the thickness of the Cotter. Okay, this is called empirical relationship. In your data book also there are empirical relationships. Okay, you'll find it, but the thing is there is a range in the data book. I mean, it ranges from suppose to 0.25 times diameter to 0.35 times diameter. So you can take 0.25 times d also. Someone may take 0.3 times d also. Someone may take 0.35 times d also. Okay, it's up to you. So that is why I told you, right? Now you see, you may think like, okay, in this case all of you will get different answers. If someone takes this one, someone will take this one, you'll get different answer, you'll get here another one will get different answer. Okay, but the thing is that is acceptable until and unless you don't go out of this range, then your answers are acceptable. Right, variations are allowed in machine design problems. Okay, so that is because of that, because it depends upon the designer and whatever he chooses. Okay, so yeah, this is the relation. Using this we'll find out the thickness. Okay, our time is about to finish anyway. Okay, so next is using this 0.31 times the diameter 32, you will get this 9.92, which is equal to 10. Okay, we'll take it as 10. Now diameter of the spigot, and now you find out all the dimensions using these formulas. Sigma t, that is the tensile failure of the spigot. If you take P divided by the failure area, if you find out, and you'll get it as pi by 4 d2 square minus d2 into t. By the way, d2 is the diameter of the spigot part. Okay, this is the failure area. Now you know the thickness, right? You know the value of this. This is 66.67. Force is 15 to 10 to the power 3, and pi by 4 d2 square minus d2 into 10. Okay, thickness is 10. From here you find out d2. So you'll get, if you solve it, then you'll get d2 as 37.91, which is, you can take it as, now see, you can think like, okay, I'll take it as 38. But sometimes in your book they have taken it as 40 also. Okay, there is no such rule. Actually you should take it as 38 is also okay for you. Okay, for me actually you can take whatever. 38 is also okay, 40 is also okay. Okay, but actually the thing is, like, for design, I can say for safety purpose, a designer, he may observe, okay, 38 is a, sometimes it may be a little bit less, so let's increase it up to 40. So what you can do is, like, to approximate these kind of values, okay, you can go up to addition of 3. Okay, up to 3. That means actually now 37.9, you have added 2.1. okay, isn't it? So you can add up to 3, okay, to get it a suitable, get to a suitable value. You will not make it as 40.5 now, isn't it? Okay, you will keep it as 40 only. Okay, you can keep it as 38 also. Okay, that means it is not bound that you have to take up 3, add 3. You can take up to addition of 3. Okay, so okay, we'll have to finish the video because of the size. Okay, so remaining parts and the remaining dimensions you can try yourself. Okay, you can try to find by the similar method. You can use all the formulas to get these dimensions. Okay, so you try yourself to find out, and we'll actually discuss all these things in the next class, and we'll solve some of the numericals before your test. Okay, and there will be your class test paper will have both numericals and theories, okay, of mostly equal portions, right? So the Cotter joint portion will will continue in the coming classes. Okay, thank you very much.